Okay, let's get started. My brain was frozen this morning. I forgot to bring an attendance sheet, so there's no attendance sheet today, which means everyone is present. Okay, let's talk a little bit about the schedule. You may have noticed that I've tried to rearrange things a little bit here. So I've added a few columns over here just to try and make this a little bit more readable. So there's a column now for the undergraduates and when your assignments are assigned, when your assignments are due, and the same thing for the graduate students. So undergraduates, you should have submitted assignment 5 by midnight last night, and we'll talk for a moment about assignment 6. Congratulations, graduate students. If you submitted assignment 10 last night, you are all done, and you can now move on to the final project. The final project is broken up into a number of weekly deliverables, so I'm afraid you're still going to be delivering something every week. The only difference is going to be it's of your creation rather than mine. And we will talk about the final project in a moment after we talk about assignment 6. All good? Okay, so let's talk about assignment 6. Okay, so for the undergraduates, you have created your first search algorithm, random search, pretty straightforward, and you're moving on to the hill climber, which we've talked about a number of times before. Remember, keep in the back of your mind, as you're developing these search algorithms, your search algorithm is searching over this fitness landscape. Remember that each horizontal dimension in this high-dimensional fitness landscape corresponds to one of the numbers in the genotype, one of the numbers that describes your robot. For the moment, those horizontal dimensions or those genes will be weights of the synapses in the robot's neural network, right? And you remember how the hill climber works. You start by choosing a set of synaptic weights at random, which corresponds to one robot or one point in the fitness landscape. And the vertical dimension in that fitness landscape is the height of that point or the fitness of the behavior produced by that artificial neural network inside that robot. Right? The tricky thing, as you carry on with these assignments, you're going to be creating more and more sophisticated robots and more challenging environments and more difficult things for them to do, is this fitness landscape is going to become increasingly rugged. So there are going to be a lot of local optima in this fitness landscape where, unfortunately, a weak learner like a hill climber often gets stuck, right? And you'll see lots of these local optima as you go. So the whole reason for this domain of evolutionary algorithms and machine learning in general is to try and find the global optima, right? The best possible behavior for your robot given a set of synaptic weights. Okay, I don't think I'll go much more into the detail. We've talked quite a bit about hill climbers and so on. Any questions from the undergraduates about 5 or 6? No? Okay, so let's talk a little bit about the final project now. So there's a link here to Del 1, which is Deliverable 1. This is the link to the final project, which I'll bring up here. So once you finish all 10 assignments, you have a basic evolutionary robotics simulator running on your machine, and that those robots are being evolved to perform phototaxis. Each robot is evaluated in 4 environments. In each of those 4 environments, the light source is placed at a different position relative to the robot. We evaluate the robot's behavior in each of the 4 environments, sum up those 4 fitness components, and that's the fitness of that robot. And on to the next robot, and so on, right? Okay, that's what you have. And it's then up to you, for the graduate students, it's up to you for the next 9 weeks how you want to expand that simulation to tackle some other problem. And it's up to you in Deliverable 1 to tell us what that problem is. I will give you a number of ideas in a moment. You can have a look at some of the robots we've talked about in this class. The subreddit on robotics is also very good for lots of different ideas. So basically, for the graduate students, you're going to be spending the next week thinking about what you'd like to tackle and then breaking that down into a bunch of bite-sized chunks. Okay. Given what you have at the moment, your evolutionary robotics simulation at the end of assignment 10 is still pretty straightforward. You have still a relatively weak learner. You have a genetic algorithm in there. There are more high-powered evolutionary algorithms than a genetic algorithm. If you want to expand the genetic algorithm into a more high-powered evolutionary algorithm, that's great. You have a relatively simple robot, this four-legged quadruped. If you want to make that the robot's body more sophisticated, that's also a direction you might go in. You might want to make the robot's environment more challenging. At the moment, all there is in the robot's environment, aside from itself, is this single cube, the light source, right? Maybe the robot needs to climb some stairs to get to the cube that's at the top of the stairs. Or perhaps there's some rugged terrain and the robot has to navigate over this rugged terrain. So whatever project you pick, you are going to be expanding either the evolutionary algorithm, the body of the robot, maybe the robot's brain. So maybe you're adding in a more sophisticated artificial neural network, or the robot's environment, or two or three or all four of those aspects of an evolutionary robotics simulation. The challenge in this class is obviously to pick something that's sufficiently interesting, but is also sufficiently tractable within the 9 weeks that you have available to do it. Yeah? So obviously for the graduate students, you're going to be breaking off a bigger chunk of something to work on than the undergraduate students. Okay, so as I mentioned, you're going to be choosing a project and then breaking it down into a number of deliverables. So for the graduate students, what you're submitting next Monday at 11:59 p.m. is 1 or 2 paragraphs, so relatively short description of what you want to do. And again, breaking it down into these deliverables. So if this is your final goal is to create robot X that performs behavior Y in environment Z, what are the 9 steps you're going to need to carry out to achieve that? Right? That's what you're submitting in deliverable 1. Okay, and then beyond that, you're then going to be, every week after that, you're going to be submitting a short video and 1 paragraph, and that video is going to be proof to us that you implemented that piece, that deliverable, right? You've broken it down into 9 pieces. Show us a video the following week that you've successfully implemented piece 1, then piece 2, then piece 3, and so on. Right? It doesn't have to be a long video. You've got quite a bit of experience now working through the 10 assignments of the kinds of things we're looking for. Right? Shouldn't take more than a 30-second video, maybe a minute, to show us that you've successfully implemented your ideas. You're not showing us video of your code because we can't read your code. You're demonstrating it through video. Okay, each one, for the graduate students, each one of these weekly deliverables is worth 2%. Your final project as a whole is worth 30%. So at the end, during our final exam period, everyone is going to be submitting a short written document and giving a very short oral presentation on your final project. For the graduate students, that oral presentation and that written report are worth 12%. For the undergraduates, it's worth 22%, because the undergrads are only going to have 4 weeks to do a final project. So 30 minus 4 times 2 is 22%. We're all good on how this is broken down? Okay. Okay, let's get on to the fun thing. Let's talk about project ideas. This is going to be a little bit more challenging for the grad students because we haven't got that far into the course yet. So you haven't seen a lot of the things that are possible in an evolutionary robotics experiment. So I've tried to put links here to some of the ideas to get you started. Undergraduates, by the 10th week, you'll have seen quite a bit of evolutionary robotics experiments, and you'll have a pretty good idea for what's possible and what's not. Some of these are projects that have been attempted, successful undergraduate projects from the past, so they give you a good idea of things that are kind of reasonable. This is from Owen. Owen took this class last year and he created a wegged robot. So as a wegged robot, as the name wegged implies, this is a robot that has legs and wheels. And you're going to evolve, in this project, you would evolve the robot to coordinate both the wheels and the legs, if you can. Okay, to get something like this. All right. Okay, so importantly, in Owen's project here, he's demonstrating not only that he's been able to evolve a wegged robot, but that this robot has an advantage over either wheels alone or legs alone. What's the advantage of this robot over just a wheeled robot? Go over barriers. So Owen's hypothesis, and this was the question he was trying to answer, is what environments would a wegged robot do better than either a wheeled robot or a legged robot? So obviously, if there are barriers in the environment, a purely wheeled robot is not going to do very well. What's the advantage of a wegged robot over a legged robot? A legged robot could presumably walk over an obstacle.
On flat terrain, it has the advantage of using wheels.
Absolutely, right? So why wheels at all? Because you can go fast on flat terrain, right? So the goal of Owen's project was to demonstrate that in the right conditions, an evolved wegged robot could be better than either alone. Just last week, some of you might have seen a physical version of a wegged robot. This is the latest creation from Boston Dynamics. Yes, the nightmare-inducing wheeled robot here. Okay. I don't know if I would really qualify this as a wegged robot. It's not really using the legs too much. A little bit, but there you go. Okay. The latest and greatest in robotics is wegged robots. You might, again, change the body of your robot to be a little bit more anthropomorphic. As you can probably see from this video, bipedal locomotion is exceedingly difficult. Why is bipedal locomotion exceedingly difficult? Balance, right? So the fitness landscape for bipedal robots are exceedingly rugged because even if you get a robot that manages to take 3 or 4 steps and then fall over, most mutations to the controller that produces that behavior causes the robot to fall over even earlier, right? So bipedal locomotion is pretty tricky, but again, if you choose this project, we can talk about some of the hacks or some of the ways you can help evolution search a rugged landscape like this, or even turn it into a smoother fitness landscape. So there are things you can do to change the simulation to actually change the fitness landscape. One of the simplest things you can do is while you're evolving gaits for your bipedal robot, whenever the robot starts to tip over, you apply an external force pushing in the opposite direction. Remember that the underlying physics engine here, Open Dynamics engine, calculates all of the forces that are acting on an object and sets the new position and orientation of that object based on those forces. You can add additional forces of your own, right? So in essence, you can kind of put training wheels on your robot, and if it starts to fall over, ODE will automatically push it back up again. As the generations continue, as evolution continues, maybe you make these compensating forces weaker and weaker and weaker until at the end, the last few stages of evolution, you're not applying any compensating forces whatsoever, right? So you're gradually telling evolution, put training wheels on your robot, and as it starts to walk better and better, gradually remove those training wheels. By doing that, you're in essence smoothing the fitness landscape. Okay, again, if you're interested in that project, come talk to me and we can talk about those kinds of things. Okay, again, we haven't got to this part in the course, but maybe you want to work on a swarm of robots. So this is my enraged swarm of Ludobots, and you'll see why they're enraged in a moment. These are just kind of random controllers, and this swarm is not really doing much at the moment. But again, you might want to create multiple robots that work together, and they're not working together very well here. They're supposed to be moving this rod together, not doing a very good job. Could you evolve a swarm to do something that's beyond the ability of any one of them? So again, you need to think about, first of all, what is this swarm going to look like, and what is their environment going to look like? Right? Okay. Perhaps you want to create a robot that exhibits some aspect of cognition. Remember, we've talked about this before. Intelligence is very hard to define, but we can sort of sit down and start to enumerate all of the aspects, all of the behavioral aspects we would expect an intelligent machine or organism to be capable of. One of those building blocks, which actually we're going to talk about in Lecture 9 today, if we get to it, is selective attention. So as you're sitting here, hopefully most of the time you're paying attention to my voice or you're reading the slides. From time to time you may look at your smartphone or take some notes or daydream a little bit, think about what you're going to do after class or tonight or with your life in general or who knows what, right? You're selectively switching your attention from time to time, which is a good thing for an intelligent agent to be able to do, right? If you only focused on one thing and couldn't switch your attention, probably not going to survive very long in a changing environment. This is, again, a project from a previous student. This is demonstrating a robot that's capable of selective attention. What's the fitness function here?
It's trying to cover as much of it with shade as possible.
It's trying to cover the hockey pucks with sensors as much as possible. But that's only a means to an end. What's the end? What's the goal here?
Don't let anything pass without seeing it.
Absolutely, right? So capture each of the hockey pucks here. What are these beams that are being emitted from the robot? These are the ray sensors, right? So you can tell what the robot sees, and you'll notice that it sees the puck on the left and cannot see the one on the right, but it remembered where the one on the right was and went back to get it. So it selectively chose, and again I'm going to use a lot of air quotes when we talk about these kinds of robots, it looks like it's choosing to pay attention to one hockey puck, but it remembers where the other one was and then comes back to collect it. So selective attention, this is a pretty tricky thing to get a robot to do. Pretty simple body, right? We've just got a simple wheeled robot here, but a pretty sophisticated behavior here. That's selective attention. Okay, there's lots of these building blocks of intelligence that you might be interested in, and especially in Lecture 9 today, we're going to talk about 4 of those building blocks, one of them being selective attention. Okay, let's see, that's one thing you might do. Coming back to the theme of robot swarms, this is a favorite project in this class. Predator-prey robots. I don't know if there's a figure. We're actually going to talk about this paper here called Evolving Teamwork. I'll just tell you what happens here. In this case, there are 5 robots, 4 lion robots, and 1 gazelle robot. The gazelle will always run away from the lions, and the lions evolve behaviors to capture the gazelle. They do not evolve the behavior to go straight towards the gazelle. Why not? All 4 lions go straight for the gazelle. Not a very good strategy, right? They might collide, right? Or make things easy for the gazelle because all the lions will converge and start approaching the gazelle along parallel trajectories. Makes things easy for the gazelle, run in the opposite direction. Gazelles, robot gazelles and real gazelles tend to be faster than their lion counterparts, so that doesn't work. Right? So the lions have to not only evolve the ability to sense and move towards the gazelle, they need to evolve teamwork. You go that way, I'll go this way. Right? Okay. So again, you can imagine this is a popular project. How would you actually evolve? Maybe just, here's an example from a student project a couple years ago. The green one is the gazelle, and the red one is the lion. I don't think either is doing particularly well. Again, this is a pretty challenging project. Actually, the lion's not doing too bad here. Oh, there we go. All right. What would be the fitness function for the gazelle, and what's the fitness function for the lion? Distance between the two is definitely going to be important to both of them. How are you going to include distance into your fitness function?
It seems like the gazelle would just try to maximize distance between you and the lion. And is there only one lion in this one?
In this one, there's only one lion, right? But you
So
could
I
have
would
multiple.
minimize distance between the gazelle and the lion.
Absolutely, right? So the gazelle's fitness function is plus D, and the fitness function for the lion is minus D, right? Which, again, works in favor of the gazelle, right? It's going to be easier for the gazelle than the lion. So how would we add multiple lions and change their fitness function so that it's not just minus D? If you evolve robots against minus D, or you evolve lions against the fitness function minus D, they're not going to do very well. What would be a fitness function that would reward teamwork? I'll leave that for you to think about, right? Those are sort of the challenges in this particular project. Okay. One other point I wanted to make about the swarm robots is, again, in assignment 10, you see how to expand your simulation so that you're evaluating one robot in multiple environments. You're now going to have to change your code to create multiple robots, possibly in multiple environments. And there's some common ways to do that. Come and see me if you want to talk a strategy for implementing that. Okay, again, we're not going to see much of this until towards the end of the course, but as I mentioned at the beginning of the course, the main difference between machine learning, or learning in general, and evolution is learning tends to be specific to the neural network controller. Evolution is not restricted to the brain, right? Evolution has sculpted our bodies, particularly our opposable thumbs, along with our brains, right? Body and brain go together. So we will later talk about a very famous experiment done by Carl Sims back in the 1990s, where he was evolving not just the neural networks of robots, but their brain, not just the neural networks, but also the bodies of the robots. As you can already see by looking at this simulation, again, this is pretty challenging, right? So you cannot no longer presuppose the number of objects and joints and sensors and motors and neurons and synapses that are sent to the simulator. The number of parts that make up the robot and their connections between them differ from one robot to the next. So again, you can imagine this video tends to be pretty inspiring. A lot of people like to tackle this particular project. I would suggest, unless you're a good coder, pick something else. Okay, I'll leave it at that for now. All right, we'll come back to Sims's creatures in a few weeks. Let's see, evolve the body along with the ANN, a more recent approach. Yeah, this was another video that went viral, I think last year, showing how to evolve bodies along with brains. Okay. Again, a pretty sophisticated project. Okay. Again, coming back to the aspects of cognition, maybe you're not so interested in the psychology side of robotics, but more the engineering or the sensor motor part of robotics. So active balance control, here's a video showing how this works. Maybe you have a robot that's walking over uneven terrain, and the fitness function is movement over the terrain, but also keep the main part of the body level. Why does that matter?
If it's storing something spillable or fragile, like carrying something across the moon, it's very fragile.
Absolutely. So maybe it's carrying an object. You want to keep the object level.
Or a camera.
Or a camera, right? You may want to be keeping a camera level. If you ever watch birds when they're walking over the ground, they will move their head in opposition with their body so that their head stays stable for most of the time that they're moving. Mammals figured out how to allow our head to bob, but you see a more or less smooth video stream if you like. Kind of a challenging thing to do. Okay, that's active balance control. That would be, I would say that's probably about a medium level of difficulty type project.
Is that the same thing as the kickable dog?
Right, so Big Dog, the famous video where they kick Big Dog and it maintains its balance. So active balance control it's related, right? So active balance control in general means don't fall over. But even without falling over, there's this added challenge of while you're moving, of keeping some part of your body level, right? So that video I just showed you is even more challenging. Yeah. Okay, maybe you want to evolve a robot capable of grasping multiple objects. This was one of my favorite robots growing up. This is from a book written in the 1980s by a famous roboticist at the time, Hans Moravec. This has sort of remained an idea. No one's been able to actually create such a robot. You can probably see why. It's a fractal, right? So every finger of this robot has 3 smaller fingers at the end of that finger. You're probably not going to create this robot inside of PyroSim, but you could make an approximation of this fractal robot. And Moravec's point about this fractal robot here is, again, if we start to think more broadly about robotics, they might have bodies that have more capabilities than what you find in nature, right? So we can copy what we see in nature, but we might, again, with advances in engineering, or in our case, evolutionary robotics, we might be able to create robots that can do things better than any human or animal can do, like our fractal robot here that can carry 1, 2, 3, 4, 5, can carry dozens of objects simultaneously. And not cheat by just grasping them like this, but actually hold multiple objects and manipulate them. Okay, I always advertise this one. No one's been able to tackle this one successfully yet. I'm looking for takers. Okay. And again, I just put here, there's hundreds of good ideas on the subreddit for robotics. If you click on the top tab, on the robotics subreddit. So you click on here on, where is it, top. You can sort of see the most highest voted robots of all times. There's some great examples in there. Okay. All right, so those are some ideas to get you started. So again, what are the graduate students doing this week? You're going to take an idea and write up a paragraph or 2 of what you'd like to do, and then break it down into 9 weekly deliverables. So I've showed you sort of what we're looking for. So I took the WAGED robot as an example. And here's the 1-paragraph summary. I wish to create a WAGED robot and test 2 hypotheses about it. Can I demonstrate situations where the WAGED robot will outcompete a similar wheeled robot or legged robot? And then, for fun, a second one, which is, does a WAGED robot benefit from more or less WEGs? So if you go back and watch Owen's WEGed robot, it actually has 6 WEGs, right? You have a quadruped at the moment. Does a 6-WEGed robot do better than a 4-WEGed robot? There's a question that you might be able to test. Okay, those are the 2 questions. So the 9 deliverables are as follows. So starting with the quadruped evolving phototaxis, turn off the phototaxis part. So we're back to just a quadruped in one environment. And then add some wheels to the bottom of the 4 legs to turn them into WEGs. That's week 1. So the video that we would expect to see is just some random quadruped on roller skates. That would be good enough, right? Deliverable 2, demonstrate the robot operating in these 3 modes. So you can freeze either the wheels or the leg joints. If you remember when you implemented joints for your robot, those joints had a desired joint range, and you could we set, I think, minus 45 degrees to plus 45 degrees. You can, in essence, clamp a joint by setting the range to minus 0.0001 or plus 0.0001, right? So turn off the wheels, freeze the legs, so now the quadruped will act like a wheeled robot. Unfreeze the legs and freeze the wheels, so it goes back to acting like a legged robot, and then unfreeze all 3. Right? So a short video like that for deliverable 2 would show us that now in your code you can easily switch between these three things. Deliverable 3, this hypothetical student is proposing to do a little bit of refactoring. So they're going to add a new variable to their constants file, and that variable can take on one of 3 values. And if it takes on the first value, the robot operates as a legged robot. If it takes on the second value, it operates as a wheeled robot. Third value, it operates as a WEGed robot. So there, you might actually just show your code. You might start a video, show us that you change that constant, and then immediately run the code, and we see that the robot has switched to a wheeled or legged or wagged robot, right? So some refactoring so that with one change to the code, just by changing that constant value, you can shift between these three different robot variants. Okay, deliverable 4, evolve some behaviors, evolve these three robots in flat terrain. Deliverable 5, evolve them in rugged terrain or with an obstacle. Deliverable 6 is trying to prove hypothesis 1, which is what's an environment in which the wagged robot does better than the wheeled or legged robot. Okay, deliverable 7, change the 4-legged wagged robot into a 6-legged wagged robot. And then again, show a new constant has been added that allows you to, just with that one change, switch between the 4-legged and 6-legged robot. And then final deliverable, show proof that either the 4-legged, 6-legged, or 8-legged wagged robot does better than the other two. Or maybe there is no difference. Maybe if you evolve these three different kinds of robots, they all do equally well. All right. Okay, that's the final project. Any questions about that? Okay, grad students, if you're thinking about ideas this week and you're not sure whether, if you have an idea and you're not sure whether it's sufficiently complex or it's too ambitious, write me an email or come and see me in office hours and we can chat about it. Okay, we'll go through the same process with the undergraduates in a few weeks' time. Okay, so let's jump back to lecture now. We're working our way through this lecture series on minimal cognition. Last time we were talking about CTRNNs, these special kind of neural networks. We'll get back to that in a moment. I taped my office hours on Twitch yesterday. If anyone is interested, you can go and have a look there. So let's go back to lecture 8. We were talking about continuous time recurrent neural networks. So the C in CTRNNs, continuous time, means CTRNNs are represented as differential equations rather than difference equations, which gives us these continuous dynamics. We gradually built up a differential equation that describes one of the neurons in a CTRNN. Remember, if we have 100 neurons in our CTRNN, we're going to have 100 differential equations, and each of the ith neurons in our CTRNN have special values associated with them. This one's pretty familiar. It's all the synaptic weights of synapses that feed into neuron I. The tau value either speeds up or slows down the rate of response of the ith neuron. Theta changes the offset, so when the value of the neuron decays down to 0, if theta is non-zero, then this neuron will decay down to theta. We put a gain on each neuron. So a gain either makes a neuron louder or quieter. What are we missing here? Tau, W, gain, theta. And then remember, in our hypothetical neural network made up of 100 neurons, a small subset of those may be sensor neurons that are receiving some value from a sensor. Those sensor neurons, this value is non-zero. So for example, if the ith neuron is connected to the first touch sensor, whenever the first touch sensor fires, this value is 1. Whenever the touch sensor does not fire, this value is 0. All the other neurons in the neural network that are not sensor neurons, this value is always 0. Okay, that's a CTRNN. And we ended last time by talking about our little humanoid robot here that was trying to hierarchically organize or sequence multiple motor primitives. So we're going to teach this robot to do a few simple things like shake the block up and down or shake the block left and right. Once it's learned how to do each of these things, we're then going to say to the robot, do motor primitive A, then B, then C, then D. We talked about one neural network model that's based on subsumption architecture, where if we're going to teach the robot 3 different motor primitives, we would have 3 different modules in the neural network, each which generates the required pattern, and then these little gates which allow that part of the neural network to take over the motors and actually get the robot to do that. We talked about the problem with this approach, which is this might work if we teach the robot 3 behaviors or 300 or 3,000, but not if we teach it eventually 3 million simple things to do. We're going to need 3 million parts of this neural network. Not a very scalable approach. So we're going to exploit the tau values in a CTRNN to create some fast neurons and some slow neurons. And the fast neurons all wired together, if they're pushed from outside in the right way, will start to produce one of these 3 motor primitives. And what are they being pushed by? They're being pushed by the slow neurons. Okay, I don't think we got this far last time, right? Okay, so here's all the nitty-gritty details. Again, this is mostly for the graduate students. I'm not going to go through all the details, but here we've got all our input-output neurons. So these are neurons that are actually affecting the motors and getting sensory feedback. Here's our slow neurons over here. We can see that the slow neurons are also being pushed from outside by the goal. So in this, for the graduate students, if you read this entire paper, goal is just a single number, which is the experimenter saying, I want this behavior now. So shake up and down, now shift left and right, now forward and back. One number, then another number, then another number. You're telling the robot what to do, one task after the other. As it's slowly being told what to do, or it's slowly being told what to do, and then this goal is changing, these slow neurons start to change their activation, and they're pushing these faster neurons to produce this pattern. Okay, I don't think I'm going to go into more of the detail. Again, for the graduate students, you can read the paper and understand this project in a little more detail. We'll just finish lecture 8 here with this picture here. So what we're watching on the horizontal axis here is the robot actually obeying the roboticist here. So you can see, first of all, the robot reaches for the cube. Now it's grabbed the cube and it shakes the cube up and down 3 times. You can see that they're plotting here, we'll forget these 2 up here. Robot proprioception, remember proprioception is the angle of the joints. So you can actually see the joints, the angles of the joints of the robot's motors changing 3 times, right? So 1, 2, 3, 4, that's probably the 2 shoulders and the 2 elbows. So it's shaking the block up and down 3 times. Then it's told to shake the block left and right 3 times. And again, we can see 3 different bumps here showing that the robot actually is oscillating 3 times. And it is actually shaking the block 3 times and then going to home. Here's some visual information as well. So it's actually, the robot is actually watching what it's doing and all's good. Okay, what are these 2 plots down here? Well, we know that the horizontal axis here is the robot actually obeying one command after the other. And the rows here correspond to I equals 101 to 101 all the way to 180. So these are actually 80 different neurons. They're not showing the first 100 neurons here. These just have to do with, the first 100 neurons are actually the sensor and motor neurons. We're going to just focus on the internal fast ones and the slow ones. You can see if you look carefully, the fast neurons are also producing some regular pattern 3 times in a row, right? Which ends up causing the motors to oscillate 3 times in a row. You don't see that pattern so much in the slow neurons here. So this is like a conductor who holds his arm at a specific angle and a melody emerges from the orchestra. Then he slowly moves his arm, and you can see there's a little bit of an oscillation here. But in essence, more or less, the slow neurons are being held constant, and they're pushing the fast neurons into a different melody or a different pattern. Okay, so these 60 fast neurons right here are capable of multiple motor primitives, and they're all encoded in that mix somehow, right? They're capable of these different behaviors. It takes some slow pressure from outside, in this case just a different part of the robot's brain, to push it into these different patterns. How many possible motor primitives do you think we could pack into these 60 neurons? You can tell from this picture that at least 1, 2, 3, 4, 5, 6 motor primitives are packed in there somehow. So the orchestra knows about 6 songs. How many could we pack in? It's okay if you don't know, nobody knows, right? It's not quite clear what the storage capacity is of this kind of neural network. Again, for those of you that are feeling ambitious, this might be an interesting project to tackle. You might remove the neural network that's in your robot right now and replace it with a CTRNN, make some of the neurons fast and some of the neurons slow. What could you get your robot to do, given that setup? Okay, I think we'll leave it there and we'll move on to lecture 9. Any questions about lecture 8? No? Okay. Okay, so as promised, we're now going to move on to lecture 9, and we're going to look at the actual minimal cognition experiments. They're minimal in the sense that we're going to look at very, very simple robots. They're not even in a physics engine. They're just in a two-dimensional virtual environment. They have a, admittedly, not quite minimal neural network. All of the minimal robots you're going to see are equipped with CTRNNs. We're not going to talk more about the CTRNNs, but just remember that's what's going on under the hood. And we're going to look at 4 different minimal cognition experiments. Each was an attempt to evolve a particular building block of cognition for these minimal robots. Okay, the first of the 4 building blocks we're going to look at is the ability to perceive affordances. If you've ever taken a psychology class, you've probably heard of this idea of affordances before. The idea of perceiving affordances is that when we, or any intelligent agent, looks at the world around it, it's not just looking at the geometry of objects and using their geometry to understand what that object is. Instead, they're paying attention to the possible relationships between themselves and that object. So here's an example. Here are 5 different objects. They have very different geometry. What do all these objects have in common? What are all these 5 objects?
Seats.
Seats. They're all seats, right? Now, you came to that answer hopefully pretty quickly because they're all placed together, right? But there's the proof, right? Geometry is completely different. You're not looking at each of these and saying, well, they may all be seats, and a seat is defined as something that has a flat piece with 4 legs, or maybe 3 legs and a straight back. That may be true for 1 or maybe a couple of these objects, but it's not that, right? Again, affordances is one of these aspects of psychology where we're reminded that thinking about thinking is misleading. If I hadn't just talked about affordances, and I asked you to define a chair or a seat, you would probably give me a geometric description, right? It has a flat seat and a couple of legs to hold it up. You would have told me the geometrical representation. You wouldn't have told me the affordance representation, which is that the definition of a seat is something that you can sit on. Right? When you look at these 5 pictures, whether you're conscious of it or not, you're mentally simulating what would happen if you tried to sit on them, right? And if 3 of the 5 caused you to fail to sit on them, you would not have converged on the answer, a seat, right? So we're always thinking, we're trying to understand the world around us by thinking about our possible interactions with them. You might not actually physically sit in that seat, but you're thinking about those kinds of things. And that's how you make sense of the world. That's how you differentiate friend from foe, right? Friend from foe, those very words have to do with your relationship between that other agent in your environment, right? Geometry doesn't matter so much. Geometry might be a clue, but ultimately it's what's going to happen if I go up and actually try and physically interact with that object, or it approaches me and tries to physically interact with me. What's the result going to be for me, right? Okay, so perceiving affordances is a very egotistical game, but you can imagine what the survival value of that process is. Okay, so just for fun, let's play the affordance game one more time. What do these four objects have in common? Obviously, I've kept one from before. They're all fuel, right? So you didn't give me a geometric description, right? Fuel. But again, it's about your relationship to these objects, right? They provide energy to you, or they provide energy for you to be able to do something, right? Again, it's always our relationship with objects. So you can see how that's important for our organisms. How is this important for robots? Well, obviously, if a robot needs to get around in the world, it's going to have to think about those objects relative to itself. Okay, so let's look at the first of these four minimal cognition experiments. Again, very minimal. Our robot is a square, and this square has two motors, which control two rockets. So this robot can apply. This robot has a C-N inside. That C-N has two motor neurons. Those two motor neurons dictate the force that's exerted by each rocket, or the amount of fuel, if you want, that's applied to the two rockets. So far, we've seen motor neurons that dictate desired angle. In this case, the motor neurons are just saying fire the rockets at this level. You can see that they're opposing rockets, so if there's a difference in force between these two rockets, the robot will start to move. Two motor neurons, 1, 2, 3, 4, 5, 6, 7 ray sensors, 7 sensor neurons, and away we go. And this is kind of another way of thinking about the minimal cognition experiments, is these are all Space Invader robots. So we've got our little robot moving left and right along the bottom of the screen here, and in this experiment we've got a pair of objects falling from above. There's the fitness function on the top right here. So like the phototaxis experiment, we're going to evaluate each robot in multiple environments, multiple trials. And each trial is different in that this pair of objects is placed at a different position, a different horizontal position at the top of the screen, and then it starts falling. We're going to take the average performance, P sub I, of the robot in these environments. So P sub I is the performance in the ith trial. You'll notice that this fitness function is actually made of two parts. So there's an if statement that's contained, an if-else statement that's containing these two parts. So if the opening between these pair of objects is too narrow for the object to pass through, use this to compute P sub I. If the pair of objects is wide enough, if the pair of objects is wide enough that the aperture is wide enough for the robot to pass through, use this fitness function. So I've told you about the robot, I've told you about its environment, and I've explained a bit about its fitness function. What is this robot being evolved to do? To go in between the blocks. Is that what we're evolving the robot to do? How do we know? Let's have a look at the first if clause here. So imagine that in trial I, a pair of objects starts falling, but the aperture, or the little hole between them, is too narrow for the agent to pass through. Then its fitness is going to be, or its performance is going to be 100 if it does not collide with either object, with the wall. And it's 2 absolute D sub I if it does collide with either of these blocks. And D sub I is the final horizontal separation between the center of the agent and the center of the aperture. So this pair of objects is falling. When the pair of objects gets to the height of the robot, we look at the horizontal distance between the center of the robot and the center of the pair of blocks. What does that part of the fitness function select for? What kind of behavior does that piece select for? The pair of objects is falling. The aperture is too narrow for the robot to get between. What should the robot do?
Move away from the center.
Move away from the center, right? So imagine that d sub I is 0. What does that mean?
It's trying to go straight to the center.
It's trying to go between the pair of objects. That's the worst possible thing that the robot could do. If d sub I is 0, then p sub I is 0 in that case. Remember, trying to maximize fitness here. What's the best thing the robot can do if the aperture is too narrow for the robot to get between? Run away, right? Don't touch either block. Okay, so we can see that when the aperture is too narrow, the robot should run away from this pair of objects. What about this piece of the fitness function? What should it do if the aperture is wide enough to get through? You can probably guess the rest of this from here.
Just get through it.
Now go through it, right? Okay, so let's try and figure this out again. So if the aperture is wide enough and the robot runs away, if it's beyond the blocks, it gets 0, right? It was the coward. It ran away when it shouldn't have run away. If the agent collides with the wall, get this piece, we'll come back to this piece in a moment, but if it gets between the blocks and doesn't collide with either block, you get maximum fitness, 100. You managed to successfully thread between the blocks as they were falling. All right, last piece. Tell me about this term. What is this term selecting for? This term is applied in the situation where the aperture is wide enough for the robot to get between, but the robot hit one of the blocks.
It's trying to reward when you get closer to the center.
Exactly.
Yeah.
Right. So we can see that we've got minus d sub I over here, right? So maybe the robot is not quite sure. It's kind of approaching the blocks and gets hit by the edge of one of the blocks. So d sub I is still pretty big, right? Very non-zero. So it takes a big penalty. If the next time around one of its descendants is a little braver and gets a little bit closer in towards the center of the pair, still gets hit, but d sub I is less because it's closer to the center of the blocks. It suffers less of a penalty and gets a higher fitness, and eventually we will evolve braver and braver descendants until they thread between the aperture. Okay, so now we've gone through the fitness function. Tell me in words, what does this robot evolve to do?
Run away from the blocks.
Not always run away.
For if it can't fit between the blocks, it will run away, but if it can fit, it's slide in between the blocks.
Absolutely, right? So if the aperture is figure out what the aperture is, and if the aperture is wide enough relative to yourself, there's the affordance piece, right? So the robot is looking at this object pair and saying, is it threadable? So one way to think about affordances is look at an object and think of an adverb for that object. It's jumpable, it's passable, it's threadable, it's beatable, it's edible, right? That tells you that you're thinking about the object relative to what you could do with it, to it, and so on, right? Okay, so if you can get through, get through. If you can't, run away, right? Okay, so now we know what this robot is being evolved to do. Let's have a look at how these robots actually did. So in all these minimal cognition experiments, we're going to actually skip over the evolutionary process itself, assume that we've run our simulation for a few hours using this fitness function, take the best robot out of the population, and let's analyze this robot. What does it actually do? So what they did is they took this single evolved, the best evolved CTRNN, pulled it out at the end of evolution, dropped it back into the robot, and then dropped a whole bunch of object pairs. They exposed that single evolved CTRNN to hundreds or thousands of different environments to see how it does in general. Okay, they did a bunch of environments where the aperture was 4 units narrower than the diameter of the robot, where the aperture was 4 units wider than the robot. And for each of those environments, they did it multiple times. So this line here shows an error bar. So the robot always did slightly different things. And the vertical axis is final horizontal separation. So this is d sub I. What did this single evolved CTRNN cause the robot to do in these different environments? How did this robot do? Or how did this CTRNN do? Okay, I see you nodding your head. Pretty good. How do you know it's doing pretty well?
Well, so the only point where it wants to have no separation is at 0, which is when it can fit. So for all the other points, it looks like there's one point after where, yeah, it didn't get all the way separated, but other than that, it's as far away as it could get. Actually, no, sorry.
Not always
I'm
as far away.
0 to 50, sorry.
Right. So we can see that the final horizontal separation was about 40 in all these environments, and all these environments are what?
Too narrow.
They're too narrow, right? So the robot did the right thing. It looked at the object pair and said, "I can't thread. It's not threadable," right? And ran in the opposite direction. And when the object pair actually hit the ground, maybe the object pair hit the ground here, and the robot was over here. This distance was 40 units, right? The robot got the heck out of there. Okay. What about the other side, the right-hand side of the graph? What's happening in those cases?
When it's greater than it needs to be, then its distance is very small because it's threading the needle.
Exactly, right? So if the aperture was wider than the robot, the final horizontal distance is 0, right? The robot saw the pair coming down, moved around it maybe a little bit to sort of figure out whether it could thread it, and then stayed there, and the objects fell on either side of it, and it did the right thing. What happened here and here? So in this condition here, the aperture was exactly as wide as the robot's diameter, which probably means it's not threadable, right? They did this multiple times. They took this pair of objects where the aperture was the same width as the robot, dropped it from here, dropped it from here, dropped it from here, dropped it from here, did it multiple times. What did the robot do in those multiple conditions?
Probably took longer for the robot to figure out if it was threadable, so it didn't get just as far as it would when it knew immediately.
Sometimes, right? So whatever it was doing, you can see these large error bars here, meaning it did very different things in these different conditions, right? Maybe sometimes it sort of looked and said, I don't know, it's not threadable, and tried to run away. Maybe sometimes it was successful, maybe sometimes it got hit, maybe sometimes it said, yeah, I think it is threadable, and tried to thread the needle and wasn't able to do so. What about this one here?
It was barely threadable, but it looks like it wasn't able to tell a couple times and went out and got a 0 on fitness.
Exactly, right? So here, it actually can get through. It's going to be a very, very tight fit, right? It's probably hard for the robot to determine whether it actually could. Maybe sometimes it decided to run away. Maybe sometimes it decided to go for it. Maybe sometimes it actually did manage to get through, right? It's a little hard to see from here. But the fact that this point lies to the right of this line is good news. It kind of means that this robot is somewhat conservative, right? If it's not quite sure, at least most of the time, run away, right? If this point had been on this side, that would be not such good news. That means this robot is maybe a little bit too ambitious, right? It decides to go for it when it probably shouldn't. Okay. All right, let's analyze this robot, this CTRNN in even more detail. Okay, takes a little bit to sort of digest this figure. So let's, again, if we're not sure about a figure, have a look at the axes first. On the horizontal axis now we have horizontal position. And this is the horizontal position of the robot relative to the center of the object pair. Right? So a horizontal position of -40 means that the pair of objects fell 40 units to the left of the robot. Horizontal position of +40 means the pair of objects fell 40 units to the right of the robot. Vertical axis is the vertical position of the pair of objects relative to the robot. So we've got our robot, we take a pair of objects and we place it 140 units above the robot, and then the pair of units starts falling. So the vertical distance starts to drop until at 0 the pair of objects gets to the ground. Okay, tell me about this figure. I'm sorry, in the left-hand figure here, this is for a pair of objects which were not passable, right? Not threadable. Why do we have all of these points starting at uniform distances along the top of this figure? What does that tell you about these trials?
Random distribution.
Not a random distribution. We have a uniform distribution here, right? What does it tell us about these multiple trials? We're bringing back our one evolved CTRNN, and we're evaluating it in multiple environments. We want to see how well it does. What does this figure tell you about those multiple environments? Yep.
At the top vertical position, they're all starting out with like a relative distance between each other.
That's right, exactly. So again, they're all, the first one, we place the pair of objects 40 units up and to the left of the robot. This pair of objects we place up 140 units up and 40 units to the right of the robot, and then they started falling. Right? So we've got the robot in the center, and we got a whole bunch of pairs that are dropping from different vertical positions, 140 units above the robot. The minute that the object pair starts falling, what does the robot start doing?
Looking for the blocks.
Does it start looking for the blocks? Now we got to pay attention to the curves of these lines. They tell us everything about what the robot is doing. What happens between height 140 and 120? So the units fall for 20 units of distance. What is the robot doing during that time?
Not much.
Nothing, right? The fact that all of these lines are all vertical means that the horizontal position between the robot and the objects is not changing, right? The robot is just sitting there. Why is it sitting there? Why isn't it acting, right? It's got to get its act together and figure out what to do.
Because the ray sensors hasn't triggered yet.
Perhaps, right? So there's a couple details that are missing. Maybe the robot can't even see the pair of objects yet. It's not quite clear. Maybe, maybe not, right? Can see what happens after below 120. So the objects are now start to fall below height 120. The robot starts moving. Tell me about what the robot is doing now.
If the starting position of the falling blocks was within plus or minus 20 units of the original block will try to find the center to see if it can fit through.
Possibly, right? So you're talking about these two inner groupings here, right? So you can see that these two inner groupings start to approach the center, right? So if the object pair is falling to my right, I move a little bit to the right, which is reducing the horizontal distance towards 0.
I feel like most of this has to do with the angle at which the sensors come out of it.
It probably has something to do with the way that the sensors are arranged, right? Remember that it's got a relatively limited field of view, right? So probably its behavior is being dictated by the limitations of its perception, what it can see. Okay. It's interesting though, right? We can already see that there's sort of 4 separate cases that are emerging here when the object pair falls below 120. The robot is kind of doing 4 separate things. There's no reason why it has to, it just happened that way. Okay, what happens about the group that's further to the left or the right?
It still might not see it and it just sits still.
It just sits still for a while, right? So it probably doesn't see those objects yet. It's just sitting still. But eventually it sees those objects, or at least it collects enough information to start moving. What does it do?
Running towards the center of it.
Starts running towards the center, right? We can see that these bunches of lines, these bunches of spaghetti, start to approach the center line, right? So wherever the pair of objects is, the robot starts moving at a uniform velocity. You can see that these diagonal lines have more or less the same slope, meaning that the robot is sort of moving at a constant velocity to get underneath the pair of objects. What happens when the robot gets underneath the pair of objects?
recognizes it can't fit and it uses its own. It seems like it uses its own momentum in that direction to keep going that way.
It recognizes that it can't fit. Be very careful here, right? Thinking about thinking is misleading. When does the robot know? When does the robot decide that the object pair is threadable or non-threadable?
Oh.
When it sees both objects.
It's not clear here, right? All we know is the robot is sort of moving underneath, right? If you look carefully, for example, let's take this group. The robot moves underneath the pair of objects, but it doesn't even slow down. It just keeps going. It sort of scans underneath and then starts to move back in the other direction, stops for a little bit, gets the heck out of there, and avoids the objects, right? So at some point, in every case here, the robot made the right decision. It decided that the object pair was not threadable and got out of the way in either direction. But it's very hard to say when that happened.
It seems like at vertical position 60, it's looking at the possibly 2, maybe 4 sensors. And if there are 2 sensors within the 2 blocks and 2 sensors outside the 2 blocks, it recognizes that it won't be able to fit.
Maybe.
But if there's all 4 inside, then it recognizes it can't fit.
That's a good hypothesis, right? You could maybe craft an environment for this robot to test exactly that hypothesis, right?
It just seems like it's waiting until it gets to that point before it makes the decision whether or not to, well, it makes the decision is a weird way of phrasing it, but
Right.
determines whether or not it should run away or not.
Maybe, right? So it's sweeping the underside of these objects, even when the objects are farts. It goes right underneath them and usually doesn't slow down. And in some cases, it reverses direction. It doesn't reverse. Yeah, it does reverse direction. Some of these, it reverses direction. Some of them, it scans, keeps going. There's probably something going on during that scan that allows it to say, nope, this is not threadable, right? Remember the British gantry robot we saw last week, right? It doesn't recognize triangles and rectangles in the way we might expect it to do, right? The way it distinguished between triangles and rectangles had something to do with the relative timing of the darkening of those circles in its visual field, right? Probably something similar going on here, right? There's something about the timing of the ray sensors, something about the timing of the shortening and lengthening of the ray sensors as it's moving that tells it something about whether it's threadable or not. Okay, we're going to take the same evolved CTRNN and we're going to evaluate it in a bunch of new environments. We're going to drop the pair of objects from exactly the same position, but now we're going to now make the aperture wide enough for the robot to get through. Same robot, different environments. What does the robot do now? Does it do something completely different?
No.
No, it's actually doing something very similar.
Yeah, it just converges to the center because they can thread the object. But I was wondering,
So it definitely converges to the center, right? We have a very successful robot, so we know it has to get to 0 in all these cases, right? The question is, how did it get there, and when did it get there?
I was also wondering if was the object changing spots it was dropped, or was the robot being changed?
It's the, I don't think it matters, but I think it's the objects. I think the robot is always in the center, and the pair of objects are dropped relative to the robot.
Okay, so because it says the horizontal position would change like all to the right or the left.
Yeah.
So I mean, if the object was like put to the left, would the robot move to the right?
That's right. So in these cases here, the object is 40 units to the left of the robot.
Okay.
And when these lines become diagonal like this and the horizontal distance is approaching 0, which direction is the robot traveling in?
Towards the object.
Towards the object. It's moving to the left and reducing the horizontal distance. Okay.
Is the width between the 2 blocks consistent throughout all of these?
Yes, it is the same. So in this case, the aperture is 1 unit narrower than the agent, and in this case, it's 1 unit wider than the agent. So the robot is actually doing, at least as far as I can see, almost exactly the same thing in all these environments up to about 40, 45, 50 units, right? So it kind of, at least to me, makes me want to say the robot made the decision at height 47, or whenever these lines start to diverge. But that's not necessarily the case, right? As you go about your daily lives, you might be looking at something and realizing it's friend or foe, and you might already have decided which is which, but you may not have broadcast the fact that you know that, right? You might hold on to that information. There's no need that you need to act the moment that you categorize an object. Same thing with our robot. All that matters is that it threads the object at height equals 0. That's all. All it has to do is get up between the blocks before they hit the ground. Right? So we can't conclude from this when the robot is making a decision, and we can't make a decision, and we can't know how it's making that decision. Okay, we got 5 minutes left. So I love the minimal cognition experiments. They beat these robots to death. They analyze these evolved robots in great detail. So let's carry on with our evolved robot, or our evolved CTNN. We're going to bring it back, and again, place it now into thousands of different environments. Each pixel in this plot down here corresponds to one environment. The color of that pixel, the grayscale of that pixel, indicates how well the robot did in that environment. So a pixel that's all white means the robot did the right thing. Gray, mediocre, that usually means it hit one of the blocks. It neither ran away nor successfully threaded the pair. And black is poor. It ran when it should have threaded, and it tried to thread the needle when it should have ran. The horizontal axis here, like up here, this is the initial horizontal position between each of the object pairs. And the vertical axis here is relative aperture width. So if you want to think about this figure, one way to build up an intuition for this figure is each of these two figures here corresponds to two rows in this figure. When the aperture is 1 unit too narrow for the object to thread between them, or one unit wider than the width of the robot. And actually many, many more cases of that. How did the robot do when the aperture was too narrow to get through? Perfect, right? So everything below the 0 is white. Whenever the robot should have ran, it always ran with maybe a couple of exceptions there, right? So again, this is good news. If we want to evolve robots that are relatively safe, we'd like them to be conservative. If you're not quite sure about the situation, run away or do something safe, right? Only engage with an object or a human if you're pretty sure about what's going on. Okay, tell me about what's going on up here.
Well, the first thing that I really noticed was that at initial horizontal position 0, it messed up a lot.
Exactly, right? So at horizontal position 0, there's this black line here. Why? Why do you think that's there? This is the best evolved CTNN from this whole experiment.
I would assume because the majority of the simulations ran with the blocks being on the side, so it's used to the first ray sensor hitting a side block. And when the initial or the middle ray sensor coming out of the robot sees the center of the two blocks, it doesn't know which side it's on, and it kind of just like goes direction.
Could be. The hint is up here, right? So you can see that these object placements, there was never a pair of objects that was placed directly above the robot. So I'm pretty sure, and I don't know if it says this in the paper, during evolution, they probably dropped the object pairs from these positions, but never from directly overhead, right? So think about the top of this black line here. This means that the aperture was 3 widths wide, right? And the pair of objects was directly above the robot. It could see this object pair just fine and didn't know what to do, right? It ran away when it should have threaded the needle. So we're going to see this a lot in the rest of this course, which is how sure are we about the robustness of an evolved machine, right? I would encourage you never to fly on a plane in which the flight software has been evolved, right? The FAA says, don't worry, we've ran this plane 100 times, and 100 times it's never crashed. It's perfectly safe, right? What about the 101st time? I don't know, right? At least in our minimally cognitive robot, in the 101st time, it crashed, and it crashed miserably, right? Some of you may have heard a few months ago about these deep learning methods, which are state-of-the-art, fantastic. There was an experiment where they actually evolved pictures to show to these deep networks. And the deep network would say, I'm 99.99% sure that's a polar bear in that picture. When you turn the picture around and actually look at it, it's white noise. There's no pattern whatsoever, right? It's because these evolved or trained machines are trained on a whole bunch of instances, but there are probably novel instances out there that can still fool them, right? This is, now not the $1 million question, probably the $10 billion question in automation, right? How can we a priori ensure that these machines that are trained on big data or evolved are going to be safe in novel situations? No one has a good answer to that one yet. Probably a good place to stop for today. You have a quiz due tonight. Undergraduates, you're now working on assignment 6. Graduate students, you're thinking about your final projects. Thank you.